In our earlier discussion in this lecture, we saw that the set of integers is countable. Now the question is whether the set of rational numbers is countable. To answer this question, let's look at a theorem. If E sub n is a sequence of countable sets, then define S equals the countable union of the sequence of countable sets. Then S is countable. In other words, the countable union of a sequence of countable sets is countable. Let's have a look at the proof. Since each E sub n is countable, we can write the elements of E sub n in the following manner. It contains the elements of this form, x sub n comma k, where k is 1 or 2 or 3, so on. For example, E sub 1 contains the elements x sub 1 comma 1, x sub 1 comma 2, and so on. E sub 2 contains the elements x sub 2 comma 1, x sub 2 comma 2, and so on. Similarly, E sub, for example, 10 contains the elements x sub 10 comma 1, x sub 10 comma 2, and so on. Since each E1, E2, so on are countable, we can enumerate these elements. Since E sub 1 is an infinite subset of S, the set S is infinite, since S is the countable union of these sets. Now we consider the function h from n cross n into the set S defined by the following relation. For example, h of 3 comma 2 equals the element x3 comma 2. Namely, this is the element in the set E3, which is the second element in the enumeration of the set E3. This function h is not necessarily a one-to-one, but is a mapping from n cross n onto S. Because if we consider any element from S, it must have the form x sub n comma k. And by definition, this is an element mapped by h with the pair n comma k. So there exists a pair in n cross n such that we get x sub n comma k. So this map h is onto, but not necessarily a one-to-one map. Two different pairs can map to a single element. Since n cross n is equivalent to the set n, there exists a map from n onto S, as shown in the following figure. Since n cross n is equivalent to n, there exists a map F which is one-to-one and onto. And we defined a map H from n cross n onto S. Then we can construct this diagram. There exists a map F inverse from n to n cross n, and we have the map H from n cross n to S. Then we can construct this map H of F inverse F from n onto S. This is an onto map. Since F is onto, hence F inverse is onto, and H is onto by construction. So their composition must be also onto. Now, by the theorem 3.2.3, S is countable, since S is infinite. This theorem has the consequence that Q is countable. Let's see the proof of this corollary. Let's define the family of subsets E sub n for each n in the following manner. E sub n is a set of all elements of the form m over n, where m is an integer. For example, E1 is the set of elements of the form 0 over 1, comma 1 over 1, comma 2 over 1, so on, or negative 1 over 1, comma negative 2 over 1, and so on. This is, in short, the set of integers. Similarly, E3 would be the set of these elements 0 over 3, 1 over 3, 2 over 3, so on, or negative 1 over 3, negative 2 over 3. All the integers get divided by the element 3 as defined. Then, for example, the set E3 is equivalent to the set Z. Since we can define a map F from E3 into Z in this way. For example, F of negative 2/3 would give you 3 times of negative 2/3, which gives you negative 2. It gives an integer. For example, suppose we want to have an output 16. We must take the element 16 over 3 in the K such that it gives us 16 over 3 times 3 equals the 16. So this is a one-to-one and onto map. Can be easily verified. In general, if we define F, the map from E sub n into the set Z in the following way, then En is countable. Because the set En is equivalent to the set Z, and Z is equivalent to the set n, since Z is countable. By transitivity, En is equivalent to the set n. This means the set En is countable. Now it can be shown that the set of rational numbers Q is a countable union of these Ens. Recall, En is a set of all elements of this form such that m is integer. So the set of rational numbers would be equal to the countable union of these sets. The proof is shown here. Now, since Q is a countable collection of countable sets, by the previous theorem, the set Q is countable. So far, we have seen that the set of integers is countable, and the set of rationals is also countable, but the set of all real numbers is uncountable. To see the proof of this, let's have a look at a theorem. The closed interval from 0 to 1 is uncountable. To prove the theorem, we will use the fact that every x in this set has a decimal expansion of the form where n sub 1, n sub 2, n sub 3, and so on are numbers either 0 or 1 or 2 or up to 9. So these are in fact digits For example, x could be an element like 0.7632513266 and so on. This element is in the set 0 to 1. However, the decimal expansion is not necessarily unique. Certain numbers such as 1/10 has two decimal expansions, namely 1/10 can be written as 0.1 with infinitely many zeros, or 0.09 followed by infinitely many nines. This, however, will not be crucial in the proof of the theorem. The proof uses Cantor's famous diagonal argument, or in other words, diagonalization argument. Since there are infinitely many rational numbers in this set, the set is not finite. To prove that it is uncountable, we only need to show that it is not countable. Recall that a set is uncountable if it is neither finite nor countable. So the set S is not finite. It is just left to show that it is not countable also. To accomplish this, we will prove that every countable subset of this set is a proper subset of that. Thus, the closed interval cannot be countable. Let E be a set of elements x sub n, where n is a natural number, be a countable subset of this closed interval. Then each x sub n has a decimal expansion. For example, x sub 1 can be written as 0.x sub 1 comma 1, x sub 1 comma 2, and so on. So recall, this are digits. Can be from 0, 1, 2, or 9. Similarly, the elements of E has the following decimal expansions. For each k in the set of natural number, x sub n comma k is in this set from 0 to n. Namely, these elements are digits. Now we define a new number, y, with following decimal expansion: 0.y1, y2, y3, and so on, as follows. If x sub n comma n is smaller or equal to 5, then y sub n would be 6. Or if x sub n comma n is greater or equal to 6, then yn should be 3. For example, if this digit here, x sub 1 comma 1, is smaller or equal to 5, for example, x sub 1 comma 1 equals 4, then y1 would be 6. Similarly, in x sub 3, if this element, x sub 3 comma 3, is larger or equal to 6, for example 7, then y3 would be 3. So we have constructed the number y out of these elements following the rule shown here. Then y must be in the set 0 to 1, the closed interval, because it has the decimal expansion 0 point some digits. And since y sub n is not equal to 0 or 9, notice here y1 possibly has the decimal expansion 0 point either all 3s or all 6s or possibly infinitely many 3s and 6s, or finitely many 3s and infinitely many 6s, and similarly. So yn is not 0 or 9. Therefore, y is not one of the numbers with 2 decimal expansions. Also, since for each n, yn is not equal to x sub n comma n, so y would not match with any of the elements in the set E, since we changed the digit, at least one digit, from each x sub n. Therefore, this new number y is not in the set E, but it was in the closed interval 0 to 1, as the set E is a proper subset of the closed interval 0 to 1. And this concludes the proof. Now we have the following corollary. The set R is uncountable. Proof. Let's assume on the contrary that R is countable. Let's assume. Since the set 0 to 1, the closed interval, is infinite, and by the theorem 3.2.2, 0, 1, the closed interval, is countable. Because the theorem says every infinite set of a countable set must be countable. Since we assumed R is countable and 0 to 1, the closed interval, is infinite, which is a subset of R, by the theorem 3.2.2, the set must be countable. But this contradicts the theorem we just proved. Namely, the closed interval 0 to 1 is uncountable. So this contradiction proves that R must be uncountable. Let's see a proposition. If a and b are real numbers with a smaller than b, then the closed interval 0 to 1 is equivalent to the closed interval from a to b. Namely, it says that the closed interval 0 to 1 is equivalent to the closed interval 2 to 7. So there exists a one-to-one and onto map from the closed interval 0 to 1 to the closed interval 2 to 7. Let's construct a map F from the set closed interval 0 to 1 to the closed interval a to b as follows. Now it's very straightforward to show that F is 1 to 1 from 0 to 1 to a to b. To show that F is also onto, let y is an element larger or equal to a but smaller or equal to b. Then the quantity y minus a over b minus a must be larger or equal to 0 but smaller or equal to 1. And f of y minus a over b minus a by definition would be a plus b minus a times y minus a over b minus a. We just substituted the quantity here into the slot of x. And this gives me y back. For every y larger or equal to a, smaller than or equal to b, there exists some element in the set 0 to 1. We get the output y. So the function f is onto. And this proves that the closed interval 0 to 1 is equivalent to the closed interval a to b. In other words, every two bounded closed intervals have the same cardinality. They are equivalent to each other. Similarly, we can use the same mapping to show that this open interval from 0 to 1 is equivalent to the open interval from a to b. And we also have the following surprising equivalence of intervals. The bounded and closed interval is equivalent to the bounded semi-closed interval. The bounded and closed interval is equivalent to the bounded and open interval. The bounded and semi-closed interval is equivalent to this bounded and semi-closed interval. And similarly, we have the last proposition.